Hey, Dr. Clark coming at you with a differential equations check your understanding video. We're in section 5.1, and that means we are looking at sort of second order differential equations, second order linear with a forcing term, modeling a spring mass damper setup. So remember the idea here, you've got a spring, you've got a mass, and that spring is going to oscillate back and forth. And if you got friction, then that oscillation is going to sort of damp down to zero. So that's kind of the context. This is F equals ma. You got your friction term here, proportional to velocity, and then you got your spring proportional to position. So as that mass gets stretched into a new position x of t, then it wants to pull back, and so the bigger the stretch, the bigger that pullback. So that's the context of this problem here. And what do they want us to do? It looks like we've got a couple of features. So we got the standard second order forced differential equation. There's your forcing term. They're saying it's some sort of electromagnet. So again, maybe we've got our spring mass damper, we've got an electromagnet over here, and that's pulling, trying to pull that mass to the right. And the spring constant is 10, the damping coefficient is 2, so we really have x double prime plus 2x prime plus 10x equals right-hand side forcing term. Okay, and if I had to look at this, I would say the friction term is quite a bit smaller than the spring, so we're probably going to get a lot of oscillation before it damps down to zero if I, kind of had my, just kind of thinking about it physically. All right, so the question says, qualitatively describe the motion for given initial conditions and then solve the differential equation. So let's take it term by term here. Part A. It looks like x of 0 equals 5, so the mass is initially 5 units to the right with velocity of 9 meters per second to the right. Okay. And because of friction, it will oscillate back to zero. Unless there is a forcing term, unless an external force is applied. And so maybe something like, if I had to graph this, it's starting here at 5, it's got an initial slope of 9, and it's going to oscillate, down to 0, something like that. Let me try that one more time. Let me do it with 2 different colors here so we can. Something kind of like that. All right. So anyway, qualitatively, something about oscillation, something about the initial position, the initial velocity. This notion of bounce kind of behavior. Okay, you can kind of think of it like that. So spring bouncing around. All right, and then to get into the math, they want us to assume that we have a constant forcing term of 20. So we've got basically 20 newtons here, and that's going to pull that spring off to the right. So we should expect that spring not to settle down to 0, but probably to settle down, somewhere else over to the right because you're pulling it with 20 newtons of force there. And they want us to solve this differential equation. So here we go. X double prime plus 2x prime plus 10x equals 20. First, I'm going to solve the homogeneous problem. So that's x double prime plus 2x prime plus 10x equals 0. The characteristic equation would be s squared plus 2s plus 10 equals 0. The quadratic formula would give you s equals -2 plus or minus the square root of 4 minus 40 all over 2. 4 minus 40 is 36, -36, so the square root of that is 6i. So this is -2 plus or minus 6i over 2, or -1 plus or minus 3i. So we're getting complex roots, and so we take those complex roots and we turn that into a solution. So the homogeneous xh of t is c1 e to the -1t times the cosine of 3t plus c2 e to the -1t sine of 3t, and that is our homogeneous solution. Part 2, we're going to need that particular solution, x double prime plus 2x prime plus 10x equals 20. Since the forcing term is constant, I'm going to assume the particular solution is constant. The derivative of constant is 0. The first derivative is 0. 10c equals 20, so c must be 2. So now my particular solution is 2, right? So the magnet is pulling with a force of 20. The spring is pulling back with a 10x, and so 10 times 2 is 20, so then you get a balance there. So my solution, my general solution would be c1 e to the -t cosine of 3t plus c2 e to the -t sine of 3t plus 2. And they wanted me to solve initial conditions. X of 0 is 5, x prime of 0 is 9. So if x of 0 equals 5, x prime of 0 equals 9, if I plug in 0 for x, or sorry, 0 for t, cosine of t is 1, e to the t is, or e to the 0 would be 1. So I would get c1 plus 0 from that sine term plus 2. So c1 must equal 3 in this case. And then I'll have to take the derivative. Now when I take the derivative, I'm going to need to be a little bit careful here. What would be the derivative? X prime of t. I guess negative c1 e to the -t cosine of 3t minus 3c1 e to the -t sine of 3t. That's the derivative of the first part. And then negative c2 e to the -t sine of 3t plus 3c2 e to the -t cosine of 3t plus 0. Derivative of 2 is 0. If I plug in t equals 0, these sine terms are going to cancel. And you're just going to end up with what? Negative c1 and 3c2. And that's supposed to equal 9. We know that c1 is 3, so basically we get 3c2 equals 12, so c2 must be 4. So now I know c2 is 4, and I can just barely write down the final solution to the initial value problem here. 3 e to the -t cosine of 3t plus 4 c2 e to the negative t sine of 3t plus 2. That is the solution to the initial value problem. Okay, so hopefully you were able to solve that problem. Give yourself some comments over here. Think about, what did you understand? What parts of the modeling here are tracking? What parts do you have questions on? And then the solving part, are you feeling good about solving for second order linear non-homogeneous differential equations using the method of the characteristic equation and the particular solution? And then are you able to find those initial conditions using algebra, that kind of thing? Give yourself a score. Hopefully you got 4, and then you should feel good. If you got less than 4, then maybe think about, what do you need to do some review on? What questions do you have? And yeah, we'll see you next time.